Hello students, today we will continue with photoelectric emission. We learnt about Einstein's photoelectric equation. Now we know that photoelectric emission is when a metal is subjected to light of sufficient frequency, which is called threshold frequency for the particular metal. And let us say the frequency is h nu, and you will find that electrons are ejected out of the metal. For that, it requires a minimum energy to remove the electron, and that is called work function. After that, you need energy for the electron to move, and that gives it kinetic energy, and you call it as kinetic energy maximum. So Einstein's photoelectric equation, what it says actually? It says that the energy of the incident photon is equal to kinetic energy maximum plus the work function W naught. We also studied using a photo tube. We have taken a photo tube and we discussed about how the electrodes are being there and how they are used and how they are functioning. Yes, let me take here, let me draw the photo tube. Okay, draw it little at an angle so that it can come an incident on the electrode. This is the photo tube, fine, and it has got two electrodes and it is connected to a cell or a battery. But I said it's a very complex diagram which you don't need now. Let us say this is negative and this is positive, and the incident light through the window comes and falls on it, and h nu is the energy of the photon or the quanta. The electrons are ejected out. The electrons reach the other plate. I call this plate P and Q, which is positive. So naturally it will attract it, and I said you make it less positive, make it 0 and make it negative, then only the electron with maximum energy will be able to reach, and when it is not able to reach and is going to come back, at that time the potential supplied is called stopping potential V naught. We know that work is equal to what? Work upon charge is equal to potential difference, or work done is equal to charge into potential difference, and here the charge is electron and the potential difference is stopping potential. So this is the potential energy. We know that kinetic energy Ke max is equal to the potential energy EV naught. Let us keep this in mind carefully when we try to find a relationship between all these things now. Okay, let me erase the board now first. Okay. Yeah. Okay. See, now these are the relationship, and I also said the work function. What is work function? It is nothing but minimum energy required to remove the electron from the metal. That is also using Planck's quantum theory. We can say h nu naught, where nu naught is called threshold frequency. So the formula will become h nu is equal to kinetic energy maximum plus, you can bring here h nu naught. Bring this to this side, h of nu minus nu naught is equal to kinetic energy maximum. Or we can say h of nu minus nu naught is equal to potential energy EV naught. These are the prime equations which we will be using. And you see here nu minus nu naught. So the incident photon should have more energy than the more frequency than the threshold frequency. That is the frequency for each emitter. Potassium, sodium, any metal you take, for example, they all will have different work function, because the electronic structure being different, and naturally it will be taking different amount. Now what I am going to do in this discussion, okay, I am going to draw a graph between kinetic energy maximum and frequency. Okay, frequency. This is the first graph I am going to draw. So let me draw the graph now. Let me take x-axis and let me take the y-axis. Okay, and this is 0, and this represents frequency which is in hertz or per cycle, and this represents kinetic energy which is going to be in joule, or precisely we can say electron volt also you can take, no problem, whichever the value you want to take. You know that 1 eV is equal to 1.6 into 10 power minus 19 joules. This is the connection between electron volt and the joule. So watch carefully here, very carefully. The frequency cannot be 0, because if it is 0 frequency incident, it will be negative. So photoelectric emission will not take place. So it has to start somewhere little away from that with a minimum frequency called threshold frequency. And you see here H is a constant, Planck's constant. So kinetic is directly proportional to change in frequency. So when it is directly proportional, it's a straight line. We are going to get a straight line, right? And the straight line, let us say, is A and B, let us suppose. Now what is the use of this graph? What is the slope of the graph going to give us? The slope of the graph. What is slope? Y value upon x value. Slope means steepness, right? Now I wanted to know y value divided by the x value. So let me take the straight line here and let me mark this point as being, yes, let me drop a perpendicular, right, at the x-axis. Let us say this point is C. At this point the frequency is nu, and at the tip here, what is the kinetic energy? For this line, this is the maximum kinetic energy. This is called kinetic energy max. Okay, you see this is the slope. Now I can write here slope of the straight line is equal to BC upon AC, y value divided by x value, that is BC upon AC, which is equal to y upon x. Now what is BC? BC is kinetic energy maximum, because we have started from origin. So kinetic energy maximum divided by, what is AC? C is nu and A is nu naught. The difference between these two, that is nu minus nu naught, that is equal to the slope of the straight line. So what is kinetic energy maximum upon nu minus nu naught? Let us come to this equation, call this as equation 1. Kinetic energy maximum divided by nu minus nu naught is going to give you H. What is H? It's Planck's constant. We can simply say Planck's constant is given by kinetic energy maximum divided by nu minus nu naught. This is one of the uses of the graph which we have drawn. We can interpret, we can get the value of Planck's constant. We can get Planck's constant from this graph. I hope you understand this. It's very simple, right? Now what I am going to do, a small change I am going to make. I am going to take the equation number 2. Here, instead of kinetic energy maximum, LHS is same. I am not worried about LHS now, right? And I am going to say that this RHS kinetic energy is replaced by potential energy. Right. If suppose instead of this graph, I am going to draw a graph between stopping potential. Now, what is the next thing I am going to do? I am going to take the stopping potential versus frequency. I am going to draw a graph between stopping potential and, let me erase it again. Yeah. Yes. Now, in this graph, I am going to take stopping potential versus frequency. Now, what is stopping potential? It is a negative potential for which the kinetic energy is maximum, or it is the negative potential of the plate for which the photoelectric emission is stopped. No photoelectric current is further coming, right? So you can define it in either of the ways. Now, this stopping potential, it stops what? It stops the photoelectron. When there is no photoelectron coming, no photoelectric current, that is what it is going to be. Photoelectric emission is taking place, but it cannot reach the plate. So photocurrent is not there. So that is what it's going to talk about. So in this case, what I'm going to do, I'm going to take potential in the V naught in the y axis, and I'm going to take in the x axis as usual frequency, right, which is in hertz, and potential, you know, it is in volt. It is in volt. Yes, this is origin. Let us take, for example, again it will be a straight line, and let us say this is the minimum frequency, threshold frequency, point A, let us say point B, we will drop a normal as usual, and this is the point C, the frequency where it is taking place, that is nu, and the potential at this point, and this is the stopping potential, the value for a particular emitter. And now again we can also calculate from this, we can find the slope of the straight line. Okay, let us find the slope of the straight line AB is equal to BC upon AC. BC upon AC, that is y upon x value, y divided by x value. What does y stands for? V naught divided by, what is x stands for? Nu minus nu naught, nu minus nu naught. Okay, so this is giving you the slope. Now what is V naught upon nu minus nu naught? Look here in this equation, V naught, we can keep it here, divided by nu minus nu naught is equal to, already h is there, okay, h, this E comes down, so h by E. It gives you the ratio between Planck's constant and the electronic charge. So the slope here gives you h upon E, whereas in the kinetic energy it gives you the Planck's constant directly, which is equal to V naught upon nu minus nu naught. Okay, this is also a problem with our equation which you can learn from this graphical representation. So now I wanted to conclude this with one small additional point here, right? These are general concepts which you have learned now in this video. I wanted to add something to this, right? And what is that actually I wanted to do it? For that we need to have the basic equation here, right? Kinetic energy maximum. Okay, let us take for example, yeah, okay, let us see here. Kinetic energy maximum is equal to h of nu minus nu naught. This is one part of it. Or we also can write it, already we wrote this, so we can express it in another way. Here we can take kinetic energy. Kinetic energy maximum is equal to h of nu minus nu naught. Now what is this actually? H of nu. C is equal to nu lambda. C is velocity of light, nu is frequency, lambda is wavelength. So I can say C upon lambda minus C upon lambda naught. Or I can also say Hc of 1 upon lambda minus 1 upon lambda naught. This also is used in numerical cases. We can use this particular equation. Yeah. Now with the graph, I want to extrapolate the graph, let us say. Watch carefully what I do here. Now leave all these parts. I am extending in the negative axis. This is minus y axis and the potential is negative. It is turning more and more negative. I extend it backward and I extend it backward like this, right? And it is coming and intercepting at the point. It is intercepting at a point there. And what does it mean here at this point? It is intercepting at this point. So this is the equation we had. Yes. Now let me take this equation, keep this kinetic energy maximum is equal to h nu minus w naught, I can say. Okay. Now what I am going to do, kinetic energy maximum is equal to nu, h nu, this thing is there. So this represent, I think I need to add some value here. Yes. I will do one thing, instead of kinetic energy, I will take EV naught. This is much better. This is what we are trying to do because this is V naught, right? So H nu minus W naught, or V naught is equal to H of E, H divided by E into frequency minus W naught divided by the same E. The work function divided by the electronic charge. You see V naught and this, already we have drawn it. Till this it has represented. And what is this? W naught upon E. This intercept gives you W naught upon E. The intercept gives you W naught upon E. Already this is represented to you by H upon E into nu, which you have done there, right? And here the intercept where it is cutting the negative axis, that gives you this value, which is a negative value. It is in the lower part of the graph, so it gives you the negative value. I hope you understand what I have taught you today. Our whole discussion was based on Einstein's photoelectric equation. That is h nu is equal to Ke max plus W naught, or h nu is equal to EV naught plus W naught. In either way, it is going to be one and the same. I have replaced the kinetic energy by potential energy. So I have done this and I have drawn graphs between kinetic energy and frequency, stopping potential and frequency, and I have taken on extrapolation and I have drawn it to you. Right? In the next video, we will see more about photoelectric emission laws. Thank you so much.